Well, hello there, folks. I hope you're doing well. In this video, we're going to be talking about Chapter 9.2, Differential Equations with Initial Conditions. If you're following along in the textbook, this does start on page 409. So in the previous chapter, we were just finding the general antiderivative. Now we're going to be looking for specific antiderivatives, or in other words, we're going to be solving for the c, the constant c. The first example, example number 1. Sorry, that's a little cut off there. There we go. Example number 1 says solve the derivative of s with respect to t is equal to 2t, where s is equal to 3 when t is equal to 0. Now, a little bit of terminology here. To solve for a derivative, so this is a derivative, right? The derivative of s with respect to t. To solve the derivative is to find the antiderivative. And since we could also rewrite this as the derivative with respect to t of s is equal to 2t, when we find the antiderivative, we're finding s. So, using the rules that we learned last time, we know that the antiderivative of 2t, or in this case s, is equal to t squared plus an unknown constant. But we want to find out what that unknown constant is. The way that we find out the unknown constant is looking at our conditions. So these are our initial conditions. S is equal to 3 when t is equal to 0. So we just substitute in what we have. S is equal to 3 when t is equal to 0. Well, when t is equal to 0, to make s equal to 3, c must be equal to 3. So our condition there is c is equal to 3. So to solve the equation, to find the antiderivative, the specific antiderivative that we're looking for, we'll now put that back into our equation right here. So the solution is s is equal to t squared plus 3. So we were able to take our c and find it, and then put it back into our original antiderivative equation. And that's what we're going to be doing for these next two as well. For example number 2, it says find the curve of y is equal to the big F of x. So curve that passes through the point -1, 0. So -1, 0. And so this is going to be the secret here, the derivative of y with respect to x is equal to 6x squared plus 6x. Well, the derivative of y with respect to x in this case is going to be the derivative of big F of x, right? So we're trying to find we are trying to find the antiderivative of this basically. So f prime x is equal to dy dx is equal to 6x squared plus 6x. So the antiderivative is equal to, according to our rules once again, so the antiderivative of x squared is x cubed. To get 6 as a coefficient, I am going to need to have a 2 initially, so I have 2x cubed. The antiderivative of x is x squared. To get 6x as a derivative of x squared, I'm going to need to have a 3 there. And then we have a constant c. So the general antiderivative, or the solution to dy dx is equal to 6x squared plus 6x is 2x cubed plus 3x squared plus c. But we want to solve for c. We want to find an actual equation. So we're going to substitute in our information here, our point. So we want the point -1. So f at -1 is equal to 0, it tells us. So 0 is equal to 2 times -1 cubed plus 3 times negative 1 squared plus c. Or another way to put it is, if we rearrange the equation, actually, you know what? Let's just solve it. Let's make things simple. So 0 is equal to 2 times negative 1 cubed. Negative 1 cubed is still negative 1. 2 times negative 1 is negative 2. Plus 3 times negative 1 squared. Negative 1 squared is positive 1. 3 times 1 is 3. Plus c. So 0 is equal to 1 plus c. Subtract 1 from both sides. I find that negative 1 is equal to c. So to find that equation, I need to put that c back into my general antiderivative equation. So f of x is equal to 2x cubed plus 3x squared minus 1, which is my answer, my function. Oh, that's equal to y, if you want to throw it in there, which is my answer. Finally, for example number 3, we have the information. Suppose that for the graph G, at every point, the derivative of that equation with respect to x is equal to e to the negative x. Find the equation of a graph parallel to G that passes through the origin. So it's passing through point 0, 0. The first thing I need to do is find the antiderivative, or solve this function. So if I go once again, so f, the derivative of big F of x, is equal to dy dx, which is equal to e to the negative x. So my antiderivative is, according once again to that table that's on page 405, on page 405, the antiderivative of this is simply negative e to the negative x plus a constant, or the general antiderivative is negative e to the negative x plus the constant. But we want a specific value, so we need to know when x is equal to 0. We know that when x is equal to 0, y is also equal to 0. So we substitute in our information. We have 0 is equal to negative e to the 0 plus c. Now, anything to the power of 0 is equal to 1. So, we have 0 is equal to negative 1 plus c, or 1 is equal to c. Easy enough. We now put it back into our general antiderivative equation to find the specific equation for our desired function. So our function f of x, or in this case, because it's dy by dx, we just want to find out the antiderivative, y, is equal to negative e to the negative x plus 1. And that's our answer. That's it. So we can use the information given to us in a question to find the actual value of c. We're going to need a point on the graph, or if it's a graph, if it's representing a real life situation, we're going to need the information like the time and the displacement, or distance, I guess is what S stands for. Whatever it is, we're going to need that information. Using that information, we can solve for c and put the c back into our general antiderivative equation to find one specific equation that relates to our situation. And that's it. Hope you found this clear. If you have any questions, please do let me know. Hope you have a fantastic day, and I'll talk to you later.